Good morning, everyone, and welcome to the IBM Qiskit Live Quantum Seminar Series dedicated to you, the academic and research quantum communities. Today is episode 120, and I'm so glad that you have joined us on time. Before we begin with introductions, we like to walk everybody over our show and how it works. And to start with my favorite question, which is, where are you guys tuning in from today? I'm tuning in from New York City. And you can reply to that in the comment chat box, which is located somewhere on your screen above, below, left or right, and is the same place where you can get questions up to Alexander and myself during this talk and presentation. In fact, we like to think of it more as a discussion, and we encourage you to post questions in the comments, discuss with each other, try to answer each other's questions, and just to keep it lively and fun. So with that, I see we have folks from New York, Oregon, Israel, France, and many different time zones. Folks, I think we might as well just get right into it. Today, I'm thrilled to roll out the latest episode of the IBM Qiskit Live Quantum Seminar Series dedicated to you. And I'm your host, Zlatko Minev from IBM Quantum Research. And I have the special pleasure of hosting Alexander McDonald from the University of Sherbrooke today. Hello, Alexander. How are you?
I'm okay, Zlatko. Feeling a little bit under the weather, but I'll be fine. How are you?
All right. Makes two or three of us here with Paul in the back. So despite that, we're going to have a great talk and a great seminar today. Allow me to introduce you, Alexander, to everyone. Alexander, who is Canadian, did his PhD at the University of Chicago with Ash Clerk. Following this, Alexander returned to Canada to join the University of Sherbrooke as a postdoctoral fellow in Alexander Blai's group. And with that, the stage is yours.
Perfect. All right. Thank you very much, Zlatko, for the kind introduction. I'd like to do the very Canadian thing first and foremost, and like I said, preemptively apologize for the sniffing and coughing that you might hear during this talk. Hopefully it'll be worth it. After all, maybe you'll learn some interesting physics. So like Zlatko said, I'm a postdoc at the Université de Sherbrooke here in Canada at the Institut Quantique with Alexandre Blais. But today I want to talk about some work that I did when I was a grad student not too long ago at the University of Chicago, where I was supervised by Ash Clark. And today I want to talk about two works which are related but different, both relating to finding exact solutions of interacting dissipative quantum systems. So in this first work I'm going to talk about, which was published last year, I'm going to show you a way to solve such seemingly difficult quantum systems where at first glance, it really seems like you have a difficult many-body quantum problem to deal with. And I'll show you there's a way, actually, using a clever trick and some symmetries, there's a way to map it onto a completely non-interacting problem where you can then solve it easily and say things exactly about the system you're interested in. And these systems I'll mention are very relevant for today's quantum computing platforms. And the second work I'm going to talk about, it's on extending a technique, a well-used and known technique called third quantization, which is used to solve a whole bunch of different problems in open quantum systems. I'm going to tell you there's a way to sort of reformulate it, if you will, which will allow us to make connections between different sorts of tools used widely in open quantum systems, which eventually will help us solve, again, more complicated problems with interactions. So again, very connected, but ultimately different problems. So before we dive right in, this is sort of a colloquium style. I'm going to focus on one word in my talk, here this word dissipative. Many of you are coming from different areas in physics, and I just want to give a very, very brief and incomplete introduction to what I mean when I say dissipative quantum system. So again, the most informal and incomplete introduction is to follow. So suppose you have some system and you want to build a quantum computer. This is ultimately going to be described by some Hamiltonian dynamics. Here we have the equation of motion for the density matrix. This is really just the Schrodinger equation written in terms of the density matrix. But of course, life is not so simple. In reality, you're going to couple your system of interest to some environment. And this environment might be intrinsic. For example, if you have spins, quantum spins or spin qubits in silicon, they're subject to some environment, namely nuclear spins. Maybe you're dealing with superconducting quantum circuits. To access the system of interest, these qubits, you're going to have to couple it to some waveguide. And this is going to introduce some dissipation. And generically, we're going to call this thing the bath. So the bath has its own Hamiltonian. It couples to my system via some other Hamiltonian. And the equations of motion for this now coupled system bath model is going to be described by, again, just the Schrodinger equation, where we have to add these extra terms sort of by hand. But this is really inconvenient. I want to do something only on the system. I don't want to have to think about what my bath, or I don't have to want to think about the bath degrees of freedom in this problem. I want to, in a sense, get rid of them. And so oftentimes, if the bath is big enough, it can absorb energy at all frequencies, which is another way of saying the bath correlation time is very small. I can do what's called tracing out this bath to get an equation of motion of this form. Again, I'm going very quickly here. Hopefully you'll forgive me for that. And there's really two features of interest here. So the first is, or really one feature of interest. So we have our normal Hamiltonian evolution. That's no problem. We understand that. The really new features that comes from having integrated out this bath, traced it out, is that it's going to introduce both noise and dissipation on our system. My variables of interest in the system are going to fluctuate. That describes this noise here. There's also going to be some dissipation, i.e. I can lose energy to this environment, to this bath. And this new feature is described by what's called a dissipator. So this dissipator, the novel part of it is that it acts now on both sides of the density matrix. So it can describe not just pure states, like the Schrodinger equation, but it really describes the evolution of going from a pure state to a mixed state. And what we do when we're dealing with the system of interest is we actually regroup all these things on the right-hand side here, and we're going to define what's called a Lindbladian. So this is now what's called a superoperator. Just like an operator takes in a state vector, spits out another state vector, these superoperators do the same thing to operators. So it takes in this density matrix, spits out another operator in my system environment, or my system Hilbert space. And this looks like the Schrodinger equation. And sure enough, we can formally solve this problem, at least, by exponentiating it in the same way we would get a formal solution to the normal Schrodinger equation. So I can do this formally, but it's not terribly simple, as I'll explain a little bit. And if you don't know this, well, the good news is that this dissipator, this x hat here, that's going to depend in principle on the microscopic derivation of the system bath coupling in the microscopic form. In practice, it's very convenient for a few reasons. So the first, note that this equation is Markovian. To find the density matrix at an infinitesimal time dt later, I only need to know the density matrix at time t. It's also what's called in Lindblad form. And Lindblad form is what's called a CPTP map. That's a fancy way of saying that if I start with the physical density matrix here, at all later times, I end up with the physical density matrix. And what does this thing represent? Well, it's really a case-by-case basis, but the good news is, like I said, it's also very intuitive. So if this operator x of s here, my system operator, is, for example, a loss operator or annihilation operator of a bosonic mode, this describes single photon loss. In the same way, if I have a qubit and this jump operator x of s is now a lowering operator for my spin, right? It takes the spin flip up to minus, well, then that corresponds to single qubit decay. And so we're big fans of this formalism in open quantum systems. And this is really what I mean here, at least in the context of this talk, when I say dissipation. And like I mentioned in the title, I'm interested in exact solutions to this problem. So in other words, you come to me with some density matrix at some initial time t0. I want to be able to find the full evolution of my system using this Lindblad master equation. And I've boxed out here the words exact solution because there might be some of you who think to themselves, well, Alexander, this is a really nice cartoon that you've drawn here, but the systems I'm working on, those are much too complicated to be described by this sort of, very basic cartoon-like interaction. Maybe, for example, you're working on something like the distance 3 surface code. So this is a figure from this Nature paper that was implemented by the group of ETH in Zurich, led by Andreas Wallraff, with some theory work actually done by some people here in Shelbhoek. And needless to say that this is a really complicated chip. I have 17 qubits, each with drive lines, flux lines, coupling elements, readout resonators, Purcell filters, and feed lines coupled to all of these things. Not only that, but in addition, these aren't really qubits. These are multi-level systems called transmons. And in fact, recent work shows that even a single transmon can exhibit dynamics reminiscent of chaos. So you might say to yourself, well, look, an exact solution to the system, completely impossible. And yeah, you're absolutely right. You have no argument from me here. But thankfully, something you might not have realized or appreciated is that an exact solution is not necessary to capture the relevant physics. In other words, all these extra elements here can be brought down to a much simpler form, i.e. some Hamiltonian and some very simple jump operators. So for example, here what they have implemented in the circuit is what's called a weight 2 stabilizer. To do this, they implement some unitary dynamics corresponding to a rotation around the y-axis, followed by an entangling 2-qubit gate via the ZZ interaction here. That describes the unitary part of the dynamics. To describe the incoherent part, they've added some jump operators, namely single excitation loss and what's called dephasing here. And in fact, only by modeling the system using this very simple Hamiltonian plus these very simple jump operators, their numerics match beautifully with the experiment. So all that to say, look, yeah, you have all this complicated setup, but it can be really described by this sort of cartoon picture I presented in the last slide. And in fact, you can show that these operations are what are called coherence limited. So it's really this dissipation down here that's to blame for a majority of the imperfections in your circuit. So it's really worth asking, even if you're an experimentalist, what can these exact solutions do for me when I have dissipation in my system? So that was more of a motivation for experimentalists. Let me talk about motivation for theorists, although maybe theorists don't really need motivation for exact solutions. But at the very least, it allows me to highlight some interesting work from a former colleague in Aksha's group, David. So David asked a relatively simple question. Suppose I have a single mode Hamiltonian where I have a Kerr nonlinearity, some detuning, and it's being driven via this funky interaction here. I then add single photon loss along with 2 photon loss. And instead of asking what's the full evolution of the system, I can simply ask, what is the steady state of this whole system? And what David found is really interesting because not only was he able to solve this problem, but it led to a whole bunch of new physics. So for example, the authors of this work, including David and a new grad student in the group at the time, Andrew, realized that you could use some of the physics they learned in this model to actually prepare single photon Fock states, and with arbitrarily weak nonlinearities. Not only that, some researchers in France, namely from Maziar Miarimi's group in Paris, realized that you can build better cat qubits. And so these authors in this work say, inspired by the work that David did here, we're going to add a detuning, tune it to a very special point. And to make a long story short, you get very special properties in the spectrum of this simple looking Hamiltonian, all again, inspired by David's work here. Continuing this line of work, David realized that the reason that this model is solvable, as simple as it is because of some new dissipative symmetries that they uncovered. So Andrew and David were able to extend this formalism, the reason that this was solvable, to some new models, namely including spins, including multi-mode systems. And they were able to show this really nice connection between normal time reversal symmetry in a classical system and this more quantum picture that you have. So hopefully in this short introduction, I've convinced you that exact solutions are interesting, both from a theory and an experimental perspective. But of course, I can't solve anything, right? Even in a closed system, I come to you with some arbitrary Hamiltonian. In general, that's not going to be able to be amenable to exact solutions. So then the question is worth asking, well, what's our setup here? What sorts of Hamiltonians and dissipation can I engineer such that the problem still remains solvable using the technique I'm going to explain to you?
Maybe
so the setup is relatively
quick question, Alexander. This is a super basic question, but on the first few slides, you grouped the imaginary term I with rho and the Lindblad. Yeah, exactly. And later slides, switch that. Is there some sort of subtle reason to do it this way here?
No. So the more conventional thing that's done in literature is what David did here, where you regroup the I on the right-hand side, and then you define, then you define the Lindbladian like such. I sort of like to do it the other way because then it's really more reminiscent of a Schrodinger equation where you exponentiate the sort of generator on this side. They're completely equivalent. You just have to multiply one convention or the other by I or minus I. Yeah, it's a great question. Sorry about the inconsistent notation here.
Okay, got it. So I guess in one case, like L is symmetric or antisymmetric, you sort of flip the symmetric antisymmetric.
Yeah. So like, for example, if I have no dissipation, L here is Hermitian, right? In the usual sense. Because I have a Hamiltonian acting on the right, I have a Hamiltonian acting on the left.
Yeah. I kind of agree with you. It sort of seems more connected in that way. So yeah.
I'm happy that one person does. I think almost everyone else in literature does
I mean,
it the other way.
It's unconventional, but I agree with you.
I'm on the crusade here, Zlatko. So. Cool. Right. And so Yes, so the setup here that I want to consider is relatively simple. Suppose someone comes to you with a Hamiltonian, which you understand well, right? And it's a little bit strange if you think about it that you understand this well, because this is, in truth, a many-body problem. I have a generalized Ising Hamiltonian, completely arbitrary couplings, Jij, completely arbitrary connectivity here. And so on one hand, this is a really complicated system because, again, it's an interacting nonlinear quantum problem. On the other hand, and this is maybe the reason why it's so simple, you have a whole bunch of conserved quantities. All of these sigma z's commute with the Hamiltonian, which means that if I start in an eigenstate of the sigma z operator, I'm going to stay in that eigenstate for all time. And so formally, I can very easily write down all the eigenvalues of the system. I can write down all the eigenvectors. They're simple product states, nothing to worry about there. On the other hand, as soon as you introduce just a little bit of loss in the system, this nice structure that you had before, where these operators are now preserved, that goes away, right? So now I'm considering arbitrary single site loss on qubit J, arbitrary single site gain. So now I can flip my spin from down to up. And then I have this term right here, which is called the dephasing term. So either term here, this one on the left or this one on the right, ruins this really nice structure that I had. For instance, if at time 0, I start in the all up state, well, there's a probability that at some later time, I'll have this spin flip, which takes me from this state to this state right here. So all of a sudden, my energy is now changed because remember, qubit J cares what this first qubit is doing under this arbitrary geometry. And so there's a competition between these J's, the rates at which all these things flip. And so you just have to sigh and say to yourself, well, look, I now have a genuine many-body problem where, like it or not, this interaction is now really complicated and ruined by even the slightest amount of very simple dissipation. So the punchline of this first part of my talk is that this is not true. In fact, there are these things which is called a weak symmetry, which can be used to find exact solutions to a very large class of interacting dissipative quantum models, including this one right here. So what's the sort of framework? Why does this work? Well, in a sense, mean field theory becomes exact. So remember, mean field theory basically says, I'm going to pretend like the single qubit is experiencing a potential, and that potential depends on all these other qubits right here. And I'm going to try and self-consistently solve this potential in the state of all these other qubits. And in doing so, I'm ignoring fluctuations. But what I'm saying is, actually, you can make this problem now exact. So now what I've done is I've removed all the interactions between the qubits. They now lie in this funny looking dissipative bath here. But the upshot is that this is really a non-interacting problem, i.e. all these qubits are really a bunch of uncoupled two-level systems. So this is a very general idea. I just want to share with you the simplest model where this sort of works. And that's given by maybe the canonical example of an open quantum system, a damped nonlinear oscillator. So here I have a bosonic mode described by raising and lowering operators A and A dagger. It has a natural frequency omega naught, a KR nonlinearity given by U. It's coupled to a bath, which means that it loses photons at a rate kappa. This bath, it has a finite temperature. And in doing so, the dissipation rate now depends on this N thermal, which is equal to the Bose-Einstein distribution evaluated at this resonance frequency. And it also has some single photon pumping. So photons are not only lost from the system, but they're also injected by this bath. And for those of you who work in circuit QED, this describes actually quite well a transmon, at least at low excitation number. Okay, so again, this looks like a relatively complicated problem, a mix of interactions and dissipation. Let's look at the physics of the closed system only. And this definitely falls in the class of the problems I was mentioning earlier. The Hamiltonian is invariant under this change of transformation that is adding a phase to this A operator. And if we wanted to be really formal about it, we'd say, well, this transformation, it's generated by this operator, A dagger A. And if I think about something like Noether's theorem, the fact that the Hamiltonian commutes, or the fact that the system is invariant under this transformation, means that the Hamiltonian commutes with this generator. And automatically, that means that this generator is now a conserved quantity. It does not change in time. That also means we can relatively easily find the eigenvectors of this thing. This simply says that for a closed system, Fock states are the eigenstates of your system. Okay, so that seems super formal, but it's worth it, I would say, because in an open system, we also have something which is very similar. L is now also invariant, if I change A by some phase. There's nothing phase sensitive in this problem. And we're going to play the same game, worded slightly differently. We're going to say this is now generated not by some operator like A dagger A, but by one of these super operators that I mentioned earlier. And the super operator is the commutator with the number operator. So there's a very close similarity between the two. And we say to ourselves, oh, well, look, this is perfect. I can now say that due to this symmetry, my Lindbladian commutes with this generator. But unfortunately, in an open system setting, that does not guarantee a conservation log like we had before, right? In fact, it's relatively clear, at least from the, for those of you who know, that this really just describes single photon loss and pumping. If I wait long enough, I'm going to reach a steady state with a thermal photon number being the average of this A dagger A. So all that to say that this is not a symmetry in the usual sense. This is what's called a weak symmetry. So weak symmetry, a concept introduced by Buca and Prozin almost 11 years ago now. And the formal definition is that it's a symmetry of this full Lindbladian, right? But not of the individual jump operators. So if I change A by some phase, well, sure enough, this jump operator does not remain invariant. So it seems like we're a little bit out of luck. Yeah, we have the symmetry, but it seems somewhat useless. That's in fact not the case. The fact that there's this commutation relation which vanishes actually tells us a lot. So I'll be a bit more explicit. I'm now going to rename this generator of this weak symmetry M. And you can show without much trouble that it has a set of eigenvectors, which is to say operators, which are just an outer product of Fock states. And the outer product of Fock states has an eigenvalue M, which is given by the off-diagonalness, if you will, of these Fock states. So for example, if P equals Q, I'm talking about a diagonal component, i.e. a proper Fock state projector, but I can have more general eigenvalues. Those are just given by the integers. And I go back and I think to myself, well, the fact that this commutes with the Lindbladian L, I can just use basic linear algebra and say that, oh, look, this symmetry allows me to write L in a block diagonal form, where each block now is indexed by this eigenvalue M. So it's very similar to what you have in a closed system. A symmetry enforces a block diagonal structure. The same is true in a closed system where I have an honest to goodness symmetry and some Hamiltonian H. Okay, so we simplified the problem at least an epsilon amount. I now have to deal with a whole bunch of smaller blocks, but they're not that much smaller. In fact, each block is infinite dimensional and describes an honest to goodness complicated interacting problem due to this nonlinearity here. And what I want to tell you is that actually that only seems to be the case on the surface. What I'm going to do now is use this generator M to effectively make the problem non-interacting. So let's focus on this non-interacting part of my Lindbladian. And what I can show is that actually I can rewrite this in this funky looking factorized form, where I've written the interaction as a product of two superoperators, the generator and some other term here in this bracket. And I think to myself, okay, well, let's go through this line of logic again. The Lindbladian commutes with this superoperator. This gives me a block diagonal form where each block is now indexed by an eigenvalue of M. And I look at my interaction and I go, wait a minute. Because of this fact up here, I can replace the superoperator M by just a number, by just an integer. That is to say, the index of each one of these blocks. And hey, look, this is amazing. I started with an honest to goodness interacting problem. And using this weak symmetry, I've now made it non-interacting in a sense, i.e. this is just quadratic in A's and A daggers. And maybe now you can appreciate why I said this was sort of like mean field theory was exact. I've taken something which was quartic in A's and A daggers, mapped it onto something which is merely quadratic. And in principle, then, this is now exactly solvable. I'll skip those details. I think it's not terribly interesting. I'll just point out a few interesting features. So we can now get the dissipative spectrum, which is to say the eigenvalues of L. And when I plot that in the complex plane, I get this interesting looking structure here. So each color here, that represents a different one of these blocks, L. And you can see that sure enough, the sort of characteristic feature of non-interacting states shows up. The spacing between each one of these complex eigenvalues is constant. And it's set by this renormalized nonlinearity and renormalized decay rate, which is now temperature dependent in general. And so these eigenvalues, I can find them. They're not just something that theorists love finding. They're actually terribly relevant for experiments. They correspond respectively to the energies of each one of these modes. and their line widths. So in other words, if I were to drive this system with some drive frequency omega d, these renormalized nonlinearities would tell me actually where I would expect to find these resonances. Cool, so that completes the diagonalization of this single nonlinear mode. And you might think to yourself, well, this is a relatively simple model. Have other people not looked at this before? And the answer is yes. So there have been previous solutions to this problem using a very, very, very different approach. So this first worked here by Mark Dickman and collaborators all the way back in the 70s, solved this problem, again, in a very different manner, i.e. in the Fock basis. These other authors, some 14, let's see if I can count, 16 years later, solved it also in a very different manner. They were looking for specific phase space solutions. And here what I'm showing is part of their exact solution. So in fact, you have two coefficients here, m and n, which is in general for the exact expressions that you would want, you'd have to sum over all of these terms. And even a single one of these terms is quite complicated. I hope you'd agree. You have some extra factor e here. You have a sum over infinite number of not only, stuff that you put to the power L, you have factorials, and then you have a hypergeometric function. So this is a little bit complicated. And in fact, so complicated to the point that some researchers actually say, well, it's easier to resort to numerics. So here what I'm plotting is a paper from 2008 by Milburn and coworkers, where they study the Wigner function of the system. And they say, look, we know these exact solutions exist. In practice, they're hard to implement on a computer. What we're going to do instead is solve the nonlinear equations of motion that describe the evolution here. And that's actually fine for us. So I don't want to denigrate in any way, shape, or form the work that these authors did. It's very impressive and elegant that they were able to find these exact solutions. But hopefully you'll agree with me that an exact solution which does not provide either simple intuition or easy to use exact results, maybe not the best thing. So what I want to argue with, or not argue, but show you is that actually our weak symmetry approach allows you to have both of these things together, an intuitive and a simple picture of the dynamics. So I'm going to present a useful analogy, which I think will be quite familiar to a lot of you. Remember, we started with this nonlinear oscillator. The complicated part is described by this Kerr interaction here. What we did is we started with the full thing and then said, okay, once we look at these specific blocks indexed by m, things become simple, that is to say quadratic. But this term here that I've highlighted in red, sort of hard to see what it means physically. If it was a commutator with this density matrix m, that'd be easy. That's just a frequency. But this anti-commutator structure, a little bit funky looking at first, really hard to interpret. Now consider another system which is used commonly in circuit QED. I have a qubit which is dispersively coupled to an oscillator. So this dispersive coupling refers here to this interaction here, where I'm saying I'm coupling the sigma z with a dagger a. Another way of saying that is my qubit frequency depends on the number of photons in my resonator. And again, we're going to focus on this part right here. And you can show actually that once you focus on the qubit coherence, which is to say, take the off-diagonal matrix elements in the qubit space, you end up with the exact same functional form as this term over here. But this, we know exactly what this corresponds to. This really means that my sigma minus operator, it's going to pick up a phase. It's going to oscillate at its frequency. But remember, the frequency now depends on how many photons I have in my oscillator. And this quantity, because of the coupling to dissipation, well, that's actually going to fluctuate. And a fluctuating phase, that corresponds to decoherence. So in this context, the fact that you have an oscillator number dependent qubit frequency, that induces oscillator dephasing, and in this context is more commonly known as measurement-induced dephasing. But we look over here and we say, oh, look, again, the structure is the same. So I can play the same game. I can say this A operator here, it's going to pick up a phase, which depends explicitly on the number of photons I have in my oscillator. And because now this thing now fluctuates, well, hey, guess what? That's going to induce some dephasing. So I'm going to call this self-dephasing. It's like, in a sense, this oscillator is trying to measure its own frequency, if you will. So to convince you that this is actually the case, I'm going to show you some nice pretty plots. Let's once again simplify the problem. Consider only a a closed system where I just have this nonlinearity U. Let's start in a very simple classical state, that is to say a coherent state, And let's evolve it at some time, right? And actually, I'll go back because I want to highlight one thing. Remember, this nonlinearity basically tells me the more photons I have, the faster I oscillate. And you'll notice right away that this fringes over here, which correspond to more photons, a higher amplitude in phase space, that's going to rotate faster. And I also should mention that what I'm plotting here is the Wigner function of my oscillator, a very commonly used phase space representation of the density matrix. So now let's time evolve this thing. And sure enough, you see that it sort of overtakes, on the outer side, it overtakes the oscillations on the inside. You have very nice rotation. There are times when it's very highly symmetric, but it seems like there's not much order going on until magically, boop, everything sort of rephases. And so you can show that if I weight 2 times pi an integer number in units of this nonlinearity, this is actually periodic. And hopefully you'll agree with me when I say that these recurrences are actually due to coherences, right? All these phases, these fringes, have to sort of match up in just the right way to recreate this result. So let's test this out. Let's maybe be a bit more quantitative by now introducing dissipation again. Of course, now we're not going to have any periodicity. That much is obvious. But let's see if this analogy that I had in the previous slide actually works, right? Let's try and increase the fluctuations in this number n and see if it leads to more dephasing. So here what I'm plotting is the average of A divided by its value at time t equals 0. This is without dissipation. So this periodic structure is exactly what I showed before. Before I showed only one of these oscillations. Of course, this repeats infinitely many times. Now I'm going to add dissipation again, and a very weak dissipation, mind you. But you see right away there's some decay. And you say, well, maybe that's not surprising. After all, I've introduced some dissipation. Photons can now leak out of my system. But now what I'm going to do is I'm going to fix kappa, fix the loss rate, and I'm going to introduce a finite number of thermal photons. And sure enough, this curve now, these recurrences are now weaker because a larger thermal photon number, that means more fluctuations in n, a larger dephasing rate. Sure enough, I can do something else. I can now increase the size of my initial coherent state. Larger coherent states, they fluctuate more. And sure enough, there's a larger decrease in the revival, the peaks of these revivals, which remember should occur at times 2 pi in these units, or integer multiples of 2 pi in these units. And just to convince you that this really does not correspond to photon loss, I can now plot both of these things at the same time. Notice here I have just a little bit of dissipation, a single thermal photon. They look very similar at the beginning, of course. Kappa is relatively weak. They play this dance, but you sort of realize that, in fact, the colors on this left-hand plot where there's no dissipation are a bit richer. They're more lively. And sure enough, when everything goes back to this initial coherent state, you realize this is really an honest-to-goodness coherent state. This is sort of like a smeared-out version. Again, this is really just due to dephasing, because if I look at the magnitude of the real and imaginary part, they're basically centered on the exact same point. And if you squint a little bit, you can see there's a ring forming around, which eventually this initial blob will spread out over all this ring and lead me to my steady state. Perfect. So again, this idea of using weak symmetries, I've gone at length about how to apply it to a lossy nonlinear oscillator. But again, it's a very general idea. Let's go through the steps needed and see how this applies to other systems. So first things first, we're going to identify the generator or the generators of this weak symmetry. And our instance here, this basically said the master equation is invariant under a change of phase of this A operator. That means that I have a super operator, which is easy to characterize, which commutes with my full master equation. This automatically, via some simple linear algebra, gives me a block diagonal decomposition of L, where remember each block does not talk to each other and is indexed by the eigenvalues of this generator. And then I use this special structure, the special sauce, if you will. We use the fact that the factorization of this complicated interaction factorized. And when I projected each one of these equations into each block, I could replace the generator by just a simple number, and I'm left with something very, very simple. I did it, this example for just a single oscillator. Trust me when I say that the same idea works for cross-care coupling, which again is quite common in current circuit QED technology, used today in many labs around the world. So now let's go back to the original problem that we had at the beginning, this dissipative Ising model. Remember, I had an Ising interactions between all the spins, some arbitrary on-site magnetic field, and then in blue here is the spin flips plus dephasing. So this problem, in fact, was already solved in a 2013 paper with an Anna Maria's Gray group at Boulder. And her group used a quite different approach. They used the quantum trajectory approach to compute all these observables. And again, it's very impressive that they were able to do it. But I want to try and convince you that this weak symmetry approach is actually a slightly easier way of doing it, even though, of course, you get the exact same results. So let's go through all our three steps. First things first, identify the generators, pardon me, of this weak symmetry. In this case, if I look at this Hamiltonian, or this master equation, you can show that L is invariant under any rotation along the z-axis for any spin. So now I have a whole collection of conserved superoperators, one for each spin. This gives me a block diagonal decomposition of L, where now instead of having just one number, I have a vector which indexes all these blocks. And something which you're just going to have to trust me on is that this superoperator, this Ising interaction, which was a complicated thing, which seemed to mess up the nice structure we had without it. When I do this projection, I get a very similar structure that I did for the oscillator case, and I get some effective new interaction strength, which depends on what all these other spins are doing. And in other words, when I look at the system, again, it looks like a complicated many-body problem. When I project now onto a symmetry-constrained block, it reduces to simple classical equation of motion of a two-level system, where I'll remind you all these J effectives now depend on what all these other spins are doing. But unlike regular mean field theory, I've ignored nothing here. This is truly exact. Cool. So this is really what I want to say about this first part of my talk. Again, there are very few examples of fully solvable many-body problems. We have what I think is a very unique and neat way to do so for systems which are very relevant to today's quantum computing platforms. And in future work, I think it'd be quite interesting to use this for more complicated problems where you have symmetry breaking terms and the problem no longer becomes exactly solvable. So I think this is a good stopping point, I would say, if there are any questions.
Yeah, maybe a quick question from Shashi in the audience here. Can we apply this method of weak symmetries to find the exact solutions of highly entangled interacting quantum systems like spin liquids?
So I would say no, but I think that's not a problem because remember that this is really a technique which works in an open system setting. So in other words, if I come to you with a Hamiltonian, which you can't say exact things about to begin with, you're kind of out of luck, right? Adding dissipation to a complicated problem is surely not going to make it easier. And in my knowledge, at least, which is relatively limited, these Hamiltonians which exhibit these spin liquid phases, you can rarely say exact things about them, except in very special limits. But if there are exactly solvable models in a closed system and you add dissipation, then yes, I would say that you'd have to check for sure, because this approach does not work for any open quantum system, but it's worth checking for sure using this recipe that I gave.
Good. Thank you, Alexander. And thank you, Shashi, for the questions. For folks, this is a great time to post more questions in the chat, and we'll always try to bring them up and share them with Alexander here. Good. I think, cool. Alexander, with that, I'll let you proceed.
Perfect. Yeah, so again, this completes this first part of my talk. And there's something that I said, which I quite honestly maybe snuck by you a little bit. And I said it sounded maybe quite reasonable, but the more you think about it, the more you think to yourself, wait a minute, how do I actually do this? And that is, how do you solve a dissipative quadratic problem? Which, remember, was really at the heart of this exact solution, because I argue that once you reduce your problem to a quadratic one, things are sort of easy. So let me be a bit more specific. So let's now remove this nonlinearity, this complicated nonlinearity that I talked about. And you might think to yourself, oh, well, this is a super easy problem. For example, if I wanted to compute correlation functions, I could do so in a super straightforward manner using this master equation. These are also easy to understand, interpret. This is a trivial problem. On the other hand, if I wanted to compute not just correlation functions, but the whole gosh darn state, that's actually a bit more complicated. In other words, if I came to you with an initial wave function, which was a non-Gaussian superposition of two Fock states, and I tell you, find the full density matrix of this thing, that's a bit more complicated, really not as trivial. You can't just solve a simple, differential equation. You have to, in principle, solve infinitely many of them. So this question here, how do you solve the full state, was actually answered by Prozin and later his colleague Seligman in a tool called third quantization. And third quantization basically says, look, give me some master equation where I have a quadratic Hamiltonian and jump operators which are linear in A's and A dagger, and I can find all of these eigenvalues and eigenvectors in a systematic method. So what I want to tell you about today is a tool, a way that we've, in a sense, reformulated this question. And the motivation behind this reformulation was, what's an intuition, a better intuition behind this procedure? Because, like I said, third quantization is already a very powerful tool. People use it for multi-mode problems all the time, where you have not just one mode, but many modes, drive, dissipation, hopping. And I argue that you need a bit more intuition because, as I'll show in a little bit, there's a surprise even for a single damped oscillator. And what I'm going to try and convince you is that not only can we reformulate third quantization, we can actually go above and beyond using all of these four things. And I'll talk a little bit about each one of these extra features of our method in a little bit. But first, I want to explain what is a surprise for a single damped harmonic oscillator. After all, it's the simplest possible open quantum system. What kind of surprises could there possibly be? So let me compare two formalisms. The first is the master equation that I told you about. Again, I'm going to vectorize the master equation. This now looks, like I mentioned earlier in the talk, like a Schrodinger equation. And just like a Schrodinger equation, you'd want to find the steady or the stationary solutions to this problem. In other words, I want to find operators now, R sub alpha and L sub alpha, which are eigenvalues of this giant Lindblad superoperator, where if I apply it to R or I apply it to L, I just get a number back. And this number, well, it's pretty easy to understand what it means physically. It controls both the energies and the decay rates in my problem. The eigenvector is a bit more hairy to understand, but that's fine for the moment. So again, these eigenvalues control energies and decay rates. Now let's turn to another simple formalism, which describes the exact same thing, but using a different language, the Heisenberg-Langevin equations, which is a simple stochastic equation of motion for this operator A, which is being driven by what is essentially the operator equivalent of Gaussian white noise. And you'll notice that, in fact, the only time temperature appears here in this Heisenberg-Langevin equation is in the correlation function of the noise. And I should emphasize, I said at the beginning of the talk, but I'll say it again, temperature appears here because N thermal is the Bose-Einstein distribution evaluated at the frequency of this oscillator with a temperature given by the temperature of the thermal bath. So I'll use both of those things really interchangeably in what follows. But this is a simple linear equation. I can solve it very easily. And once I have the solution, I can very easily compute correlation functions, multi-time correlation functions even. And this is, again, exactly equivalent to this master equation here on the left. But then I say to myself, wait a minute. If I look on the right-hand side here, nothing ever oscillates or decays in a way which depends on N thermal. The oscillations and decay rates are controlled only by omega naught and this decay rate kappa. So looking at the left-hand side over here, I say, well, these two formalisms should give me the same correlation functions. So I'm forced to conclude that actually the eigenvalues which control the energies and decay rates are completely temperature independent, which is a little strange at first. I come to you with this master equation, which again, you can think of as some big matrix. And I tell you, no. Actually, the eigenvalues are completely insensitive to N thermal, which appears both in this loss dissipator and this pumping dissipator. So that's a little strange, and it's really worth understanding why this happens. On the right-hand side, it's super clear why it happens. This temperature-dependent term only appears in the noise. So I think it's worth asking, well, forget about the eigenvalue problem for now. How do you identify noise at the superoperator level in this master equation? And so I'm going to argue that there's a very simple way to do so via what I'm going to call the classical and quantum superoperators. So these are now just definitions at this point. The quantum superoperators take this form. The classical superoperators take this form. You'll note that this definition means that I have A's and adductors acting on both the left and the right of the density matrix. And what I can do then is retake this master equation that I had that I know well and rewrite it in this basis. So completely equivalent. And I've written it in this very special form here because I'm going to argue that this first line here, that corresponds to the dynamics. And the second line here, that corresponds to the noise. And unlike regular sort of standard second quantization, I'm going to have some funky looking number superoperators where now I can think of this term right here as an operator which tells me how many quanta I have in some specific mode. And this other term here also tells me that same thing, but in an independent mode. So these are really number operators for two independent particles. And this is not just a, something that I came up with. This is really why, constructed by Prosen originally. And this is really why he called it third quantization. But of course, he did it in a slightly different way. So the construction of these states is actually very similar to how you would do it in a regular quantum system. You have a Fock state, right? How do you build Fock states? You say, okay, look, my annihilation operator A here, that kills this reference state, which I call the vacuum. If I want to have n particles in the state, I apply the conjugate variable A hat n times to this reference state. And then almost by construction, I say, look, I have n particles. This is an n photon Fock state. Here I can do the same thing almost mechanistically. I have some reference state, which A classical and A classical dagger now kill using slightly macabre terminology. And I can build up these number eigenstates in the exact same way that I did for Fock states. But now the interpretation is I have mu particles and nu holes. And there's an analogous construction just for completeness. There's analogous construction for the left eigenvectors. Great, but this all seems for naught because what I've done essentially is I've only diagonalized, if you will, this part here that describes the dynamics. So what I'm saying is that if I apply just this superoperator that I've put in a square here, I apply it to these operators that I've defined. Sure enough, I get just a number back. So that's great. That's what we want. On the other hand, you can convince yourself that this is not an eigenvector of the noise here. In fact, the noise is going to couple many of these eigenstates. So you think to yourself, well, that's sort of a bummer. Why did I go through this whole procedure? Until you remember the original motivation for finding the master equation in this basis. Remember, we argued that I should be able to sort of eliminate the noise, right? Because the eigenvalue should be temperature independent, right? And so in some sense, I should be able to sound maybe overly fancy, gauge away this term entirely in the master equation. And what I mean by that is I'm going to define this new superoperator V, which I can think of as like a basis transformation or a similarity transformation. And by that, I mean, when I apply V, I conjugate it to this original superoperator L that I care about. I'm going to come back with the dynamics. So this is completely untouched. And that's it. There's no noise term. I removed it entirely from the superoperator using this new similarity transformation. And I'll remind you that these two objects right here, well, these were the superoperators that we identified as number operators. We know how to get their eigenvalues. And look, L and this object right here, they're related via some invertible transformation. Sure, it's not unitary, but that doesn't matter. That means they have the same eigenvalues. So I can then right away write down the eigenvalues of my third quantized Liouvillean as such. And I'll remind you that the temperature did not vanish here. The temperature lies entirely in the similarity transformation, or in other words, entirely in the eigenvectors of this problem. And we show in our paper that this is not a fluke. In fact, for all linear models of bosons and fermions, the fact that I can get rid of this noise is really the consequence of some new dissipative symmetry. Great, so this is, completes the somewhat quick diagonalization procedure of the single mode, and we can recover the results in Prosen Seligman, which I'll remind you was the first paper on this formalism. But we can actually do a little bit more, actually much more. Using these new things that I've introduced, the phase space formulation of quantum mechanics, that is to say, the Wigner function, actually appears very naturally. So that's a little bit strange at first glance. I've told you about how to find these discrete objects, these discrete left and right eigenvectors. Where does the continuous nature of phase space show up at all in what I just talked about? And the answer is naively, well, absolutely nothing. But I'm going to ask a very natural question, which really has a very simple closed system counterpart. Just like I can ask the question, what are the eigenvalues of A, that is to say the coherent states, I can ask what are the eigenvalues and eigenvectors of all these new superoperators that I've introduced. So I'm going to skip a little bit of math. I promise you these things are not hard to find and describe. In fact, if you take in a quantum optics class, you know what they are. They're just displacement operators and displaced parity operators. The important point here is maybe 2 or 3 things. So first, aclassical and aclassical dagger have the same eigenvectors. That's fine. Remember, they described different modes. A-quantum and A-quantum dagger, same sort of story. The really important part, however, is that unlike coherent states, which remember have a finite overlap between coherent states of different amplitude, that is not the case here. Different classical eigenstates are orthogonal to other states of the same kind, and same thing for this object down here. And that really means I can think about the density matrix in the quote-unquote wave function of these new bases. Let me be a bit more specific. I can take the density matrix in this sort of funky third quantized form. I can now write it as a sum over all these terms right here, right? All these eigenvectors, just like I would in regular quantum mechanics for a position eigenstate or position wave function representation, for example. And then I can compute, again, using directly the formulas which are analogous to the construction in first quantization, the quote-unquote wave function in this basis. And if I look hard enough and I finesse this expression a little bit, trust me when I say that this is exactly the Wigner function of a harmonic oscillator, something that is very well known in standard quantum optics. And we didn't go looking for it. I really want to stress this is something that comes very naturally from our formalism. And if you want to think about the Wigner function as sort of like a position space wave function, well, consequently, these new objects I've introduced are sort of like position space eigenkets. And you can play the same game for these other types of superoperators, where you can show that the wave function is actually another well-known object, the characteristic function of this oscillator. And since these two are related to each other via Fourier transform, and this is a position space eigenket, well, consequently, I can think about this object as like a momentum space representation in phase space of my density matrix. So that's kind of neat. It also, you know, it's very naturally, or I should rephrase that. I can say that this actually comes about very naturally because if I look again at the third quantized representation of L, and I look at the Schrodinger equation, I can then write down the equation of motion for rho very directly. And there's a direct connection between this dissipation term right here, which describes dynamics, which again corresponds to the drift term here in the equation of motion for the Wigner function. And this noise term here that I called noise before, that has a direct correspondence to diffusion in this phase space representation. Perfect. So that's kind of neat. And this connection, to my knowledge, at least was not known before. But you might think to yourself, well, you're sort of reinventing the wheel. What new can you do with this formalism that you couldn't before? Great question. I'll answer it in 3 different ways. So there's 2 sort of unsatisfactory issues with the results I just showed. So the results I showed were, of course, correct, but maybe we can build a little bit more intuition by thinking about things in phase space. So if I think about the steady state of this oscillator problem that I just described, it's very well known that it's a Gaussian. It's a Gaussian. Its width is described by this temperature-dependent term. On the other hand, if I look at the steady state written in the formalism I gave you, you can show that it's equal to this strange-looking object on the right here. And that's super weird. I have to find this steady state by applying an infinite number of nested commutators with A and A dagger, acting on the parity operator. I mean, that's just a mess, no matter how you slice it. And even if you could show this result formally, it really doesn't provide any intuition whatsoever. So that's the first problem. The second problem is, how do you think about this right eigenvector, which ideally you'd like to think about in connection with Fock states? Because remember, this object has a well-defined decay rate, and there should be a minus sign here. This object has a well-defined decay rate of kappa times mu. And again, I like to make the connection to a simple Fock state, but that's just not the case. In fact, if I compute this quantity explicitly in its second quantized form, it takes on this form right here. And I've looked at this for a very long time. I can't find a simple connection between this and a 2-photon Fock state. So I'm going to try and convince you in the little time that I have that these issues are actually very much resolvable by looking in phase space. And at first I realized, wait a minute, this object that I introduced, this is now diagonal in this basis of operators that I introduced earlier. Because remember, by definition, I could just replace a quantum, or this term right here, just by a number. And so I can work with this just by using numbers, and I'll skip through the full calculation, but trust me when I say that if I want to know what the Wigner function is of this new density matrix, the one where I take V applied to my old density matrix, I want to know what its phase-space wave function is. That corresponds to convolution of my old wave function with this Gaussian form right here. So that's kind of cool, something that, again, was not known before. And this also matches our intuition, because remember, when I had this third quantized representation, this V, this similarity transformation, was designed explicitly to remove the noise term in this equation, which means, using our phase-space formalism, this V removes diffusion. And remember, when I convolve something with the Gaussian, that tends to sort of smooth it out in phase space. And diffusion has the same role. It basically sort of spreads things out in phase space. So what this is saying is if I pre-convolve, in a sense, my wave function of interest, I don't have to worry about it at all in the dynamics anymore. So I'd argue that this is now a satisfactory issue. I can put a check mark. And then I can ask a similar question for the second problem that I posed, right? What is the connection between these two things, which at first glance look very different? And again, I'm going to go to phase space, where I know, for example, that the Wigner function of a Fock state takes on this form. So this is a Gaussian factor times something called the Laguerre polynomial. It's not terribly intuitive, but when we compare it to the wave function of these new, eigenvectors of our Lindbladian that we found, hey, look, these things are almost the same in phase space, very different in their second quantized representation, but they're essentially the same. And then a little bit different, I have to rescale this phase space variable by some amount to take care of the temperature dependent term. But even then, there'd be a difference between the Gaussians and the arguments of the Laguerre polynomials. More details maybe than is necessary. But I think this is a much cleaner way of seeing that these two things are actually very closely related and take on the same functional form. So I see that my time is almost coming up. I'm going to go very quickly over one more thing, which I think is super cool, which is how to use what I just described to get a new type of path integral. So remember, this object here, this A-classical, alpha classical, I should think about it as like a position eigenket in phase space. This object right here, that defines time evolution. And so this whole thing right here, that's like a propagation amplitude. That is to say, if I start at this very particular point in phase space, what is the amplitude of ending up at some other point in phase space? Beta. And you can derive a path integral, just like Feynman did for position and momentum space, regular path integral that we all learn in quantum mechanics. The sort of catch is that this is now a dissipative path integral. And so this action takes on a very special form called the Keldysh action. But unlike regular Keldysh field theory, I'm going to be able to say something about all times here. In other words, this propagator here gives me the full information about the time evolution of an arbitrary state. And actually, this is what I used when I was showing these plots earlier. So we can apply it to this nonlinear oscillator problem. I don't want to belabor this expression, but look, this is a very clean, compact expression for what at first glance seemed like a very complicated problem. And this is the exact formula that I used when computing this Wigner function for this oscillator here, i.e., this thing right here is exactly what I'm showing in this GIF. Perfect. So, I'm very much aware that I've introduced lots of new concepts in the last, 20 minutes, way too much for any reasonable person to absorb. And that's 100% fine. I don't expect you to have absorbed all this, so just forget that for a moment. The really big picture I want to leave you with is really that you can connect using third quantization, this new version of third quantization that we've introduced. You can connect three different things, which at first glance look very, very different. And that not only provides some sort of, I would say, fundamental relation between the three, but it provides you something very useful because, again, you can relate it to, you can use it to solve, at first glance, complicated, non-interacting problems. So I think I'm running slightly over time. I'm just going to flash out my conclusions. Thank you very much for your attention, and I'd be more than happy to answer more questions. Thank you.
Thank you, Alexander. This was really great. Folks, a great time to post more questions in the chat. And maybe actually there's a good opportunity to go back to the introduction of the new A quantum classical operators and maybe just kind of help us understand the motivation for defining those particular structures and forms. I think you had it after the comparing of the two formalisms where, yeah, because I guess, is this another way of saying that you're picking some operators to factorize to do a quadratic factorization of this super operator terms in some way, and then, or how do we understand and motivate that these are the ones that you should have chosen to pick, or one should choose to pick,
Right.
and write down?
Yeah. So good question. Maybe I should have been a bit more clear. So remember, this is a quadratic problem. So there's no nonlinearity at this point. I'm just dealing with something which is quadratic and A's and A daggers.
Mm-hmm.
So the motivation is, you can maybe define it several different ways. I think the end motivation is that it just sort of works. If you have this definition, you get a clean separation between what constitutes the dynamics and what constitutes the noise. For example, if you have a multimode problem now, so imagine a lattice of these oscillators with hopping, with coherent drives, with loss, you can always, using these definitions, rewrite this third quantized Lindbladian, separating these two terms, something which describes the dynamics, i.e. this is the energies and decay rates of my problem, and then separate it in this noise term. And furthermore, if I go back to the Wigner function,
maybe how, in what sense is this the noise term? Because okay, even if n term was 0, there's still a kappa there, just like there's a kappa in the upper line. The only difference is that you have a QQ here as opposed to a QCL.
Yeah.
So it's not very transparent what that means.
Yeah. So even if n thermal is 0 here, like you said, you still get this term, this +1. That really corresponds to if you want quantum noise, because even if I'm coupled to 0 temperature bath, there's still quantum fluctuations that come into play. And maybe the simplest way of saying it is that, remember when I made the mapping from this super operator to the Wigner function, this term right here, that's the thing that describes drift and dissipation. This term right here, that describes diffusion, right? So diffusion, again, I can really think about that as noise. This is something which takes me something which is very localized in phase space and tends to spread it out. That's how I think about noise. I don't think about it as, oh, look, this is what sets the oscillation and decay rates in my problem. So I think it's much more transparent to start with a finite n thermal, right? And then via the argument I made in the previous slide, nothing should ever oscillate or decay at this rate. And so this necessarily then describes the noise.
Okay. And if I had nonlinearity, would I still want to use these operators to begin the description? Like, are they sort of the super operator equivalent of A and A dagger? That
Good
makes
question.
sense.
Yes. Yeah. You definitely would, because then actually this factorization that was so important in the previous, first part of my talk actually becomes super apparent. In fact, this is how I came about finding out, this first part of my talk. I actually used these super operators written in this form, and then it became very apparent that the structure was there. So absolutely, yeah. But I didn't go through that just for time purposes, yeah.
Okay. And in that case, I'll have some higher order polynomials in AQ, ACL that are sort of have an equal number of Qs and Cs.
Exactly. Yeah. Yeah. So exactly right. You'd have something which is not quadratic in A's and A daggers with these classical indices. You'd have something which is quartic, but you'd still get this factorization term, and that's what makes it, in a sense, solvable.
Okay. So anything that has a QQ is noise, basically.
Exactly. Yeah. Yeah. And you can show. I'll say one more thing. So in this nonlinearity, when you add this nonlinearity, there's a term where you have one classical and 3 quantum terms. And that is what's called quantum noise. So you cannot have that at a classical level. It truly describes to something which has to do with quantum fluctuations in phase space. But if you have a classical nonlinear oscillator, you'd have terms, for example, which have 3 classical terms and 1 quantum. That's allowed classically. So you can really cleanly separate out what exactly is quantum or not quantum about your coherent dynamics.
And what are terms like ACL, ACL?
ACL, that's a great question. This is related to this observation right here. You actually cannot have ACL terms because that would violate conservation of probability. And it's a little bit tricky to show to see why that would be. Maybe I'll go back. So this is like an anti-commutator. Sorry, this is a commutator.
Yeah.
you'll notice that all the quantums here are on the left of L. So I think it's a too high a level, but L here is trace preserving, right? So in other words, if I act this on any density matrix row, right, the trace of this new object vanishes. And a classical term would violate that property. Because essentially, if you want to think about it, you'd have an anti-commutator of A with rho, but here you have a commutator, and so that sort of vanishes. It's not hard to see or obvious automatically, but it guarantees conservation of probability.
I see. It's still a little tricky.
Yeah, it's like I said, it's big picture. I hope that the big picture was sort of clear, but the details you definitely need to.
Does this also apply to spins?
So spins. So this classical quantum mapping. To my knowledge, no. So to my knowledge, what people do is something a bit more conventional. So the first thing you would do if you were given a super operator like this, right? You'd say, forget about this notation where I act on both the left and the right. I would just define a super operator. Let me call it A sub L, which acts only on the density matrix from the left, let's say, or acts only on the density matrix from the right. That's maybe a bit more natural way to think about it. And that's what people do with spins. But there's not this clean separation in spins between this quantum and this classical term.
I see. So you're saying that this somehow has to do with the structure of the ladder up or the bosonic system.
Yeah,
and if I have qubits or spins, then it doesn't make sense to define this, because I could also define there, a super operator that acts from the left and the right.
And this is exactly what a quantum is, right? It acts on both the left and the right of the density matrix. Yeah. And if you have dissipation, then of course, maybe that's not so crazy to do, since you're going to have to deal with that anyway.
Yeah. But you're saying that you wouldn't really, it wouldn't probably be useful to define these kind of operators for the spins. This is really more for bosons.
Yeah, I don't think so. Yeah. But maybe I'm wrong, but to my knowledge, people don't do that. Yeah.
Okay. Interesting. Okay, good. That's and I think let's see. There's a question also from Shashi of, can you use this separation of method of the noise, this way of thinking about it, somehow think about error mitigation or encoding information in some protected ways?
That's a great question. We haven't really thought about that. We've mostly thought about using this as a way to do perturbation theory and sort of separating out there. The dynamics and the noise is actually quite convenient, especially when you have nonlinearities and you can really identify quantum noise, because if you have a large amplitude coherent state, for example, you can often argue that you can ignore this quantum noise term. But maybe coming back to the original question, I haven't thought about that, but that's an interesting point of view.
Okay, good. I think, folks, this is a great moment to post any final questions you have. I know we're here almost 10 minutes over with Alexander. This has been a very nice and interesting presentation, because you've really introduced quite a few, new concepts and ways to look at, a whole set of
yeah. Hope it wasn't too much.
Yeah. of things. So definitely very stimulating. And maybe just in the last minute here, I always like to open up the floor, Alexander, for you to share any final thoughts or ideas or messages or advertisements you want with us and the audience.
I can't think of any off the top of my head. Maybe thank you very much, Zlatko, for organizing this. You said 120 episodes. That's quite a lot.
Yeah, this is 120, I believe.
Yeah. And Paul, of course, in the back for also doing this 120 times. So thank you very much.
Excellent. Well, with that, there's lots of nice messages in the chat saying, great talk. Thank you. And it's great to see great minds coming out of Canada. So with that, Alexander, thank you very much for accepting our invitation. And folks, I hope we have enjoyed the latest seminar. This seminar with Alexander will stay recorded and live here on the Qiskit YouTube channel. So you can always go back and watch different parts of it. But only Friday at noon Eastern time. You can tune in live with us and ask questions and interact with speakers and ourselves. So with that, folks, we will see you next week and the one after. I'll be on vacation next week, so maybe Maria or someone else will be hosting if we have the seminar. And with that, hit the subscribe button and see you Friday. Fridays at noon Eastern Time.